Yes, okay. Welcome to the session for AI, machine learning, and data science for transportation. I am Mostafa Ameli from University Gustave Eiffel, and I will be chairing this session. We also have Sebastian Romolo coordinating the Zoom session and helping us with the technical issues. We have a very interesting set of presentation covering several applications of AI in transportation, from computer vision and vehicle profiling to machine learning and travel behavior. For this session, we have five presentations scheduled. So as I sent an email to the presenter, I kindly ask that all presenters respect the allocated time, like 20 minutes, that we can keep some time for question and discussion, and maybe we have some time at the end for discussion about the session topic and if there is any remaining question. So without further delay, we can start. Let us start with the first presentation. Daming Wang will present multi-stage framework for vehicle profiling from traffic video using object detection and vision language models. Daming, the floor is yours.
Okay, thank you so much. Can you all hear me? Yeah, okay, thank you. Hi everyone, my name is Dami Wang and I'm from University of Victoria under Civil Engineer Department under supervision of Dr. Laura Minute. And today my presenting topic is a multi-stage framework for vehicle profiling from traffic videos. First of all, why we came up with this project is because we are doing a vehicle emission testing as my whole PhD project, but when during this process, I found out like this is a small project I need to focus on because we want to study vehicle emissions from only cameras, as cameras placement and resolution significantly can affect the performance in objective detections, especially for vehicles on the road. And since we don't have the specific license plate information, so we don't have the very detailed information from the ICBC, which is the license plate management vehicle department in our city, and so we don't have any of the vehicle informations from the license plate. So we are thinking of a way from directly observing information from cameras, and so we need a very detailed, fine-grained solution to identify the vehicles. So this is whole uh, framework of how we did it. First of all, we take the video input and then we decide which is a high angle uh, surveillance angle or a street level cameras, as they have different resolutions of high resolution and low resolution, and then route them to the right model to detect the vehicles in with classifications of large types like sedan, SUV, trucks, pickup trucks, etc. And then we will do a track and count process, like assign unique ID to each vehicle, and you get the count and speed of each vehicles. And then using the correct errors, a multi-frame correction process to vote for the correct type to increase the vehicle detection accuracy. Then finally, a AI detection identification process using a visual language model to look at the photos and identify the make, model, and their estimated year range. And then we can look up into the other United States EPA vehicle dataset and also some other datasets that include the vehicle information for each make and model and year, like fuel economy, weight, and emissions, etc. So here is how we do it with a string-aware expert routing. We're using a ULO model, which is a you only look once model that is widely used in object detecting industry, and it is can be used to identify each trained and identified in each scenarios as a gate classifier to route those videos into traffic expert or street expert. And then they are trained specifically on each different data sets. And MIOTCD is a dataset as a Canadian and United States surveillance angle training set. And the Objective 365 is a large data set that has many different type of vehicles, including sedan, SUV, and even including sports car and ambulance, etc. And here is how we got as a result of classifications. We can see the MIOTCD got generally higher accuracies of identifying using ULO as a almost 85 percentage. And for the street expert, as it is very difficult to identify and label them correctly as the street level has more influence as the background, like people going by, and the background is more complex. So it is generally lower, slightly lower as a 60 percentage. And here is how we do as a uh, ULO detection model and using them as some on some vehicles we have monitored on the road. And however, it seems like the accuracies is not that high because in real scenarios, because we can see it can usually classify the SUVs as small cars and also the pickup trucks as SUVs and the sedan cars as a pickup trucks, which is absolutely wrong. So we need to refine them to increase the accuracy. And here is how we did it. But it is inspired by temporal aggregation, but simpler and domain specific. And it can track every video across frames in the whole videos. And it can using a commonly used tracking algorithm called BikeTrack, and which is assigned a unique ID to each vehicle. And when the vehicle is passing by, each frame are studied and identified individually. And so the refinement system can vote for the most constant and highest possibility classification results and multiply by the weights. Here for a image, we can see it more clearly as it is identified as a car in the first two frame, and then an SUV and a car, and then SUV in the following frames. So it is more highly possible that the SUV is more possibly it's the real results. And it can also multiply with the weight because as the vehicle is getting moving in the frames and it can be getting larger and larger in the cameras. And when it's more larger, the accuracy would be more accurate. So the weight is a little bit larger for that frame. And here is our multi-frame specific classification result. We increase the misclassification result from 47 percentage to 77 percentage, which is a nearly 30 percentage improvement across 789 vehicles in 8 videos. So it is really impressive to show the misclassifications here, but we successfully increased the accuracy of misclassifications, especially on car and SUVs. As we can see here, it's really a misclassification samples. And what we will do next is vehicle type alone is not enough because even after the vehicle type identifications, the SUV and sedan classification is still not enough because same SUV class can expand from 200 to 50 to 500 grams of CO2 emissions per mile, and it is nearly 2.5 uh, m more than the plain SUV emissions. So it is really not enough for a identify as only an SUV. So we need more on very detailed fine-grained level. So we are thinking of a VLM approaches to identify without a license plate. And previously, the VLM approach is mainly based on the text-based AI motivated pipelines identify the are their license plate and match them to the uh, vehicle management department. And however, it is not possible in our case. So we are thinking of a more general way and a more widely used way to identify the make and model. So our approach is using direct VLM prompting and no plates and no extra training and getting a very high accuracy. And here is how we did it. We used mainly two VLM models, which is Gemini 2.5 Flash cloud based and also a Gemma 3 local based model, a VLM model. However, it seems like the local based VLM model is less accurate and it cannot identify much more like rare vehicles. Uh, it can only identify most of the commonly seen vehicles. And for the Gemini 2.5 Flash as a cloud VLM model, it can have more information of online and it can also search their own Google search image search database. So it is much more accurate of a nearly 99% of accuracy. And so here is how we do it with a prompt input of a structured JSON. So we specified it as a JSON file, and then output the make, model, year range, and body type, and also some visual cues to inspire the model to identify them. For example, like the uh, very unique light, and also the pumper style, etc. And then match the output with the fuel economy database and the CVS database, which is a database including their vehicle weight and dimensions. And here is how we do it and what is the result of our identification. We can see that the local model of Gemma 3 is only accuracy of 60%. However, a Gemini 2.5 Flash got an accuracy of 99%. And it has only three errors of two Mercedes submodels errors. It cannot identify whether it is a GLE 350 or a 450, etc. And also a model misclassification of Model Y and Model X. And the cloud VLM has the access to web scale knowledge, so it is a benefit. However, it is really limited to a cloud usage only right now. So we're also thinking transition to a local model and trained and self-learned by and guided by the online model. As a local model, it can be much cheaper and low cost and also a accurate one. And here is how our YOLO prediction classes and compared with the EPA vehicle classes of the class confusion. So we can get that almost most of the vehicles are correctly identified, but still are some misclassifications of the sedan car and the SUVs. And especially those are the misclassification of the hatchback and the SUVs. So we can see here the YOLO is not that accurate compared to the VLM. And here is how our framework results from only one video. So we can get the vehicle count and speed and the vehicle type with refined vehicle type results from our program, and also a make model year results from the VLM process, and also fuel type and fuel economy results from the matched database, and also the engine displacement, vehicle dimensions, curb weight, and estimated CO2 and many other lab test vehicle emissions results from only one videos. So here is what we can do to improve in the future, like using fine-tune smaller local VOM to close the accuracy gap and the cost gap, and also retrain YOLO on misclassified cases like bad capped pickups and hatchback sedans. Those are the most misclassified cases. And then they validate the speed estimation using a GPS ground truth and add weather adaptive process for rain and snow conditions. So we only now focusing on the day and night videos, but without like those extreme weathers. And what we can do next is extracting all the information from one single video and using the information to train a prediction model on pollutant emissions. So after we have got all of the make model year informations, we can further train our vehicle emission predicting model, as each vehicle type and model are performing really differently. And so we can see here using a RSD, which is a roadside device, to get the pollutant emission data, and also combined with other vehicle information and weather information and the vehicle cold start status and geographic conditions like the road slope, etc., to train our emission models. So and that's basically all of my presentation. And the applications of this project is just with a limited informations we have got, so we can train our we can acquire information from only one video and use them to get all the information of each vehicles, and can be used on vehicle analysis and also other areas like emission testings in my case, and further informations. Yeah, that's all of my presentations. Thank you so much. And any questions?
Thank you very much. Thank you, Deming, for this interesting presentation. So now it's time for questions. Please feel free to put your questions in the chat, or if you want to raise your hand, if you have question for Deming.
Oh, yes, Kara.
Yes.
Oh, yeah. Raise the
Thank
hand.
you. Thank you for allowing me to unmute. Yeah, I entered a little bit late because I was busy helping out with the keynote today. And I was wondering if you could show us what kind of video you had, because I've been using cell phone and dash cam video. So the camera's moving to try to identify plate and other things.
Oh, yes, I can absolutely answer that, but sorry, I don't have the videos on this computer right now, so I cannot show you, and it's kind of information it's kind of as a I it's not shareable. It's still have the license plate and maybe some faces, but my videos used are basically dash cams and also a on-site cameras of pointing to the rear vehicles. So for the dash cams, they still can be trained and using a bike track. And for the license plate identification you mentioned, I can imagine it would be much harder because the dash cam resolutions are the most top uh, thing I can think of. So it could be a little bit harder. But in my case, it's basically a make model year, which is larger, much larger object to identify. So I think it's much better. Yeah. Did
Yeah,
that?
year is really nuanced. I don't think we've been able to identify year, but if you can get, make model year won't help the police, find these people, but license plate or a portion of it certainly will. And we've created a little tool that people can upload video or photos and tell what the issue was that they thought they were seeing, as well as take a guess at the license plate and the make and the model and the color. Color is pretty easy, fortunately, and that's enough for the police or other enforcement agencies to work with to try to talk to the owner to see who was using the vehicle at that time. And so I'll put that into the chat box, but yeah, I would love to get in touch to kind of strategize on these tools so that we can make roads safer is the reason we're doing this work.
Thank you so much for sharing. Thank
Sure.
you. Yeah. For the question of Jason, I can answer that. Other LLMs, I have, sorry, for the other LLMs, I have tried them, but they are generally performed really bad. Like I have tried QN 3.5 and but with a much smaller model and also other models like ChatGPT and also uh, Cloud Opus, but they are generally performing bad and they are much more expensive. For the QN, it is a local developed model, but it's need much larger local requirements as needing more hardwares, but they are generally performing bad because Google Gemini got the database of Google image search, which is their benefit. And Google image search, you can use them on the phone like the Google Lens. They are the same thing. So they have that benefits of much more accurate results and generally cheaper price. Yeah, thank you. And
And yeah, the next question is why you use Gemini 2.5 Flash?
yes, thank you for the question from Brandon. This is generally like similar with last questions, but Gemini 2.5 Flash was the model I was using at that time, back in half of a year before. And at that time, this is the cheapest cloud usage model I can think of from Gemini family. Yeah. And I have explained the reason not choosing other VLMs other than Gemini families. Yeah. I think that's kind of answered that question. Thank you.
Okay,
Uh,
thank you very much. And thank you, Professor Kalkelman, for sharing the related website and studies. So now we can move to our second presenter.
yeah.
Thank you, Doming. Uh,
Thank you so much.
Lorenzo Munoz Torrejon will present analysis of choice model and machine learning algorithm performance using machine learning metrics. Lorenzo, floor is yours.
Yes, thank you so much. Can you see my screen here? And can you hear me okay?
Yes. Yeah.
So can you see the presentation or the
Uh, you have to change the display setting to.
perfect. Sorry, one second. It's gonna be there you go. Can you see this now?
It's still in the
Ah, I see, I
present.
see, I see. So I'm just gonna share the full screen. Is that better?
Yes.
Perfect. Okay. Thank you so much for having me. I'm Lorenzo Munoz. I do my PhD here in Leeds, and I'm going to present the work that I've been doing with my supervisors, so Stefan Hess, Thomas Hancock, and George Sphere. And it's essentially using information criteria from machine learning, the machine learning field, and apply this in choice models and also in machine learning algorithms. So the bit of background is the motivation. Uh, a big question in the literature is what can we choice modelers, and this has several applications in transport demand. What can we learn from machine learning modelers? And oops, I did something. I don't know what happened. Can you see my screen still?
Yes. It's in
Okay.
the background motivation slide.
Okay, perfect. So in choice modeling, model performance has historically relied on log likelihood, which is, an aggregate measure of it, and that focuses only on correct predictions. So in the probabilities of the chosen alternative. Um, and there are plenty of more different metrics, but that rely also on log likelihood, such as AIC, BIC, likelihood ratio test, etc. And there's limited attention on what we can learn from other fields in terms of the information criteria that we can get. So essentially what we do is we introduce, probabilistic machine learning metrics, but we apply this into choice models. So what we have is essentially accuracy, sensitivity, specificity, and balance, and I'm going to introduce them briefly. But one of the contributions is that the probabilistic outputs actually preserve information that many deterministic outputs discard. So one of the golden standards in the machine learning field is actually to use deterministic predictions. So to take the highest probability as the predicted alternative. So therefore, we discard some valuable information there. And the reason to use multiple metrics is that these metrics capture different things, right? So we've seen accuracy, I think, was reported in the previous presentation, but there are many metrics that focus either on correct predictions or incorrect predictions, and sometimes misclassifications or different types of misclassifications can have different different weights in different applications, for example, in medical procedures or so. And another motivation is to compare, so say the training and testing confusion matrix to analyze for which specific alternatives we can detect overfitting, which is also a big issue in machine learning. So these are I'm not gonna spend a lot of time here, but these are the traditional performance metrics that we use in choice models. So what we have here is log likelihood, for a given set of parameters beta, the summatory of the logarithm of the chosen alternatives and how the models recover it. But we also have the likelihood ratio test to compare different models, again, based on log likelihood, adjusted rho squared, again, based on log likelihood, AIC, BIC, etc. But what we traditionally do in machine learning as well is come from this basic example, which is the binary confusion matrix with two classes or alternatives in the choice modeling vocabulary, so to speak. So what we have is essentially a positive and a negative alternative, and we have predicted classes and observed classes. Now, as I said before, this is typically deterministic. So essentially what we would have in the inputs of this matrix are counts. And therefore in the diagonal what we have are correct predictions, so true positives or negatives for each alternative, but also false predictions, which are the false negatives and the false positives. Now, what we have applied in this context, in the choice modeling context, is first, a probabilistic extension on this, but also a multi-class confusion matrix. So imagine we have three alternatives. Imagine we have car, bus, and walk. And for a given car observation, we have different probabilities for all available alternatives. So again, assuming that all alternatives are available, say we have a 0.5 probability of actually predicting car, a 0.3 probability of predicting the alternative bus, and a 0.2 probability of predicting walking. So this is the way the observations and the probability vector for each observation is distributed in the confusion matrix. So then, for each observation, we would start summing up all the probabilities that we obtain eventually, and then obtain as the inputs or as the outputs of the confusion matrix, the whole sample size eventually. But more specifically, from this confusion matrix, the multi-class one, we can also obtain different cases, as we said before. So for a specific alternative, so say we're talking about the car here, we will positives in this value, and then we will have the false negatives here. So when car is observed but not predicted, we'll have the false positives here, so which is when car is predicted but corresponding to a different alternative observed. And then all the remaining cases would be true negatives. So this is quite similar to what was, just presented in the confusion matrix from the previous presentation. And from these metrics, we can obtain, from these outputs of the confusion matrix, we can obtain different machine learning metrics. And as I said before, these are not mutually exclusive, but rather complementary. So what we would have is accuracy, which is arguably the most widely used metric in the machine learning field to evaluate performance, which is essentially the true predictions divided by the whole set of the confusion matrix. But we would also have sensitivity, which focuses on true positives, but out of all the positive observations, and conversely specificity, which is true negatives divided by the whole negative observations. And lastly, we would have balance, which is, has been reported as a metric that is more informative in balance settings. So say in a data set where some alternatives are quite overrepresented and some alternatives are underrepresented. So we apply this in a very famous data set, I would say, is the Swiss Metro data set, which was conducted by Michel Virler in Switzerland in 2001. 10,728 observations and 3 alternatives. So train, car, and Swiss Metro. But here we also have the shares of each alternative, where we can see that Swiss Metro has, the highest share of the choices, whereas train is the minority alternative, as we call it. We used 80% of the data for training and 20% of the data for testing, with also a validation subsample within the training set of 20%. And then we estimated many models on many data sets. I figured I would present these ones as this is a machine learning session. So I'm going to present the results on the XGBoost that we conducted, a neural network, random forest, and also an MNL, because this application is more on choice models. So these are the confusion matrices that we obtained for each of the models that I just introduced. Essentially, what we have is the observed alternatives here: train, Swiss Metro, car; predicted alternatives: train, Swiss Metro, car. And I've normalized the observations by the row. So essentially, each row sums up to 1. And I've also presented both the training and the testing confusion matrices for all models. And interesting insights come just by looking at the confusion matrix, where we can note that, for instance, for the MNL, well, for all models essentially, but importance application in the MNL is that when for train observations, Swiss Metro is predicted this 62% of of the time, or essentially has a probability of 0.62. And you know, for the car, also for the car alternative, also the share of Swiss Metro predictions are quite high, which is something, again, we wouldn't be able to understand if, you know, by looking at aggregate metrics such as log likelihood, etc. Then, when we turn to the random forest algorithm, we can see that the diagonal elements are quite higher than for the MNL and than for all the other machine learning algorithms as well. And also the off-diagonal elements are decreased, which is, again, a good thing that we have here. One of the other observations I wanted to make here is that it has been claimed widely in the literature how machine learning algorithms outperform choice models in terms of predictive accuracy, say neural networks, XGBoost, etc. And, you know, yes, but I've also seen that they report many times the deterministic outputs of this, and only the deterministic outputs. So when we turn to, you know, also probabilistic outputs, we can see, well, there's also some decrease, you know, when we look at the neural network. So the neural network is actually worse for predicting the train alternative than a basic MNL, basic, you know, linear in parameters, not a very sophisticated model, and so on. And same happens with the XGBoost. So we have more misclassifications here for the car observations when predicting Swiss Metro. So that's I mean, that's one of the takeaways here. And also, when we look at the metrics themselves, we can find some interesting things as well. So first thing, here's the, well, alternative specific metrics, models, training and testing. And we can see that the MNL and the XGBoost have a very similar overall accuracy, but very different log likelihoods. So then the probabilities of the chosen alternatives in the XGBoost are actually higher. Just as a takeaway, as a you know, as a finding of what accuracy can mask by looking solely at overall accuracy. When we turn to the alternative specific accuracies and metrics here on the MNL, for instance, we see that the train alternative has a super high accuracy, to be fair. And, you know, this was the alternative with the minority alternative, so we wouldn't expect this. But when we look at the sensitivity here, again, the which one that focuses on true positives, this is, you know, quite low. So one of the other takeaways here is that we should focus on multiple metrics rather than solely on accuracy, etc. And then specificity is quite high, so that's the contribution of true negatives again. Also the, you know, the predictive performance shown in the confusion matrix by random forest is supported here by the out of sample log likelihood and also accuracy. So yeah, you know, the main takeaways of these are allowing people in the choice modeling field to look at the results by the different alternatives. So to look at which alternatives are poorly predicted and then, you know, targeting improvements in model specification. So saying the utility function of the alternatives that are being poorly predicted, you know, incorporating variables or non-linearities, etc. We can also penalize performance for incorrect predictions, which is something we don't do in log likelihood, so to speak. Again, substitution patterns, as we saw on the train observations that were frequently misclassified as the Swiss Metro alternative. And, you know, I didn't include this in the results because we conducted a hyperparameter search and all. But when looking at the confusion matrix of testing against training, we can see actually in this hyperparameter search for which specific alternatives we're currently overfitting. And another takeaway is that we can have very similar aggregate metrics such as log likelihood or accuracy, but then have very different confusion matrices. So what we can, you know, we can achieve the same overall predictive performance, but through very different probability distributions. And one of our next steps is to automate model specification. And there's has been some work on this, but again, based on AIC or some of these criteria. But what we want to do is actually to maximize the diagonal elements and then minimize the misclassifications, so the of the diagonal elements of the confusion matrix via an algorithm that automates model specification. And then that is what I had prepared for today. Many thanks for your attention. I'm just going to stop sharing now because I can't see the chat. So I'm just going to go to the Zoom meeting now.
Okay, thank you, Lorenzo, for this interesting presentation. We have a couple of questions. First, from Adnan, which predictor are used to train the model?
Yes, what do they mean by predictors? Is it the variables in the model or?
It's
And
for
then
training.
for the
Yeah.
second question, if we ensemble models such as model, doing something like model averaging or something like that, definitely yes. But then that's kind of out of the scope of this. Maybe we can achieve higher accuracy. Our aim so far is just to understand what is going on in these models, and potentially, yeah, we can improve this via ensembling models. And then regarding variables, basically all the variables available in the Swiss Metro dataset, which is basically level of service, so travel cost, travel time, headway time, etc. And some covariates, some user covariates, so income was there, occupation was there, something like that. But it was of the order of 10 variables. We do have way more complex data sets with many, many more variables. But I figured just for the sake of this presentation, it's easier to present the results like this. Please email me if you have any more questions on this.
And next one from
Yeah, from Samuel Hassan. The data differences are statistically significant. This on a single test. So you mean as in, well, I'm gonna start with the second question. So do we estimate on a single test set or multiple test set? We conducted a k-fold cross-validation, which is essentially basically changing the testing set. So it was a 5 k-fold cross-validation. So we tried 5 different testing sets, if that's what you mean. So I just presented, the first one we had. They didn't change very much, so we just left some. The results were very similar, so we left it like that. And then, what do you mean if the differences in what are statistically significant, Samuel?
So I think we have to conclude
Yeah,
maybe at the end. If we get more time, we will back to the
absolutely. Yeah.
discussion. Thank you again. So now we can move to our third presentation from Sepehr Golrokh Amin, that he will present zero-shot travel diary generation using large language models. Sepehr, please go ahead.
Good afternoon, everyone. Can you see my screen now?
Yes.
Perfect. So thank you. First of all, thank you for the opportunity to present our work. My name is Sepehr. I'm a PhD student in transportation engineering at UConn. So to make the most of our time today, I'll go ahead and get started. This study asks a practical question for activity-based modeling, which is, can a general purpose large language model generate a good daily travel diaries without being calibrated on a local household travel survey or not? So the motivation is not that the traditional activity-based model are ineffective. Their strength is precisely that they impose statistical and behavioral structure. The challenge is the amount of local survey data and calibration effort they often require. So our research question is to see to focus on more narrower question and see if using a large language model can come up with a plausible one-day diary for a synthetic person when it receives only public, demographic, and built environment context, which I'm going to explain in the next few slides. And importantly, in our case, that we evaluated these on Connecticut survey data that we had access to. So the Connecticut travel survey is not used to teach or fine-tune the large language model. It is held back for validation and for calibrating the comparison benchmark. So that's separates make this a genuine zero-shot test of activity generation. So the experimental design keeps the input for generation separate from the evidence used for evaluation, as I said. So we use the 2015 ACS to create local demographic profiles and the EPA Smart Location Database to describe the built environment. And these data sets are linked at the census block group level. The ground truth, on the other hand, as we had access, was 2016 and 2017 cities, Connecticut statewide transportation study. So we processed more than 2,000 block groups and generated one personal day diary per block groups. So this gives broad geographic and behavior coverage while keeping the study focused on activity generation rather than the full population synthesis that many softwares use for the ABM modeling. And it's not the objective of this study, the population synthesis is not the objective. So the framework has 4 main stages. First, the code loads the ACS and smart location data for a block group and synthesize a plausible persona. Employment, age, income, and vehicle availability are sampled conditionally, while household size is derived from the local population to household ratio. Second, then the persona and the neighborhood description are passed to a locally host llama tree model through OLAMA, which has been trained by Meta. And the response is parsed, checked, and saved in a standard form of CSV for further evaluation. So the prompt is constrained enough to produce consistent data, but open enough to let the model reason about behavior. It includes the list of modes and purpose that match the survey data dictionary, so we can compare them in a proper way. And the model returns a weekday diary, as I'm showing us 3 samples here on this slide. So the decoding parameter are, for example, adjusted by the employment status. So employed personnel receive slightly more diversity, while unemployed personnel receive more conservative settings. So the example table on the right is showing 3 diaries for 3 different person. Like person number A, we have low walkability index there, and that person is employed with upper middle income. Person number B, medium walkability, unemployed, but younger. So, and we are seeing different diaries for each one of these. So the classical benchmark, on the other hand, is calibrated directly on the household travel survey. So daily trip frequency is modeled with negative binomial regression because the observed count data are over-dispersed, and modes and purpose are modeled with multi-nominal logistic models. So, the LLM, in contrast, as I mentioned, received no study-specific training or calibration. So both models start from exactly the same number of block groups to do the population synthesis for the diaries synthesis. Our main methodological contribution is the one-to-cohort realist score. For each generated diary, we find a cohort of comparable people in the household travel survey using up to 6 variables: age, employment, vehicle count, income, block group, identifier or geo ID, and household size. If fewer than 10 observed persons are available, the matching rule is going to be a little bit loose. So this way we make sure we have more than 10 people in our groups for comparison. So for the validation metric, we use JSC, which stands for Jensen-Shannon divergence. In simple terms, it measures how different two probability distributions are. Here, P is a distribution from the match household travel survey cohort, and Q is the distribution from one generated diary. JSC is useful, and we picked that because it's symmetric, bounded, and remain valid when a category appears in one distribution but not the other. We converted the divergence into an intuitive similarity score using 1 minus JSC. So a higher score means a closer match. And we use this measure for trip purpose, travel mode, and activity intervals, as it is shown here. And trip counts use a relative error score, and the 4 components are averaged to obtain the overall realist score for one-to-cohort validation. For aggregate validation, we compared the full set of generated diaries against the entire HTS population to assess the macro level patterns. Same formula, but for trip count, as is compared the distribution across all personnel rather than a single value, the trip count score is compared using JSC2. So the results. At the person level, the LLM achieved a mean overall realist score of 0.692 compared to 0.628 for the classical benchmark. The paired difference is statistically significant at the P level below 0.001, and the LLM distribution is also narrower. The standard deviation is about 0.075 versus 0.115. So the classical distribution contains a secondary lower scoring group, while the LLM scores are more concentrated, as you can see in the shape of this figure. I would interpret this result carefully. It doesn't mean that every LLM diary is correct. It means that under the proposed 4-component metric, the zero-shot diaries are on average more similar to their match survey cohort. The component score explains why the overall result should not be reduced to a single winner. So the calibrated classical method are stronger on trip count and activity intervals as shown in this figure. That is expected because the negative binomial model is designed for count data, and the benchmark is fitted to observe survey distribution. The LLM's strongest result is trip purpose and mode choice, where it constantly outperformed the multi-nominal across all matching levels. So in plain terms, the classical approach is better at numerical regularity, while the LLM is better at semantic relationship between who the person is, or where they live, or why they are traveling. The aggregate analysis pools all generated diaries and compares their distribution with the entire household travel survey population. So the LLM reached at aggregate overall score of 0.779 compared with 0.706 for the classical benchmark. Its largest advantages are in trip purpose and mode choice, as we are seeing here. The classical benchmark remains strong for activity intervals. This supports the claim that the LLM captures broad population level travel patterns. So two robustness checks are especially useful. First, the LLM remains ahead when the four realist components are weighted. So the direction of the comparison is not an artifact of equal weight. We check that. Second, the complete framework was run 7 times. Mean trip frequency and trip distance change very little. The mean pairwise aggregate similarity was 0.9968. Even so, several limitation remains. First one, the empirical evaluation is limited to Connecticut because we had the survey data for Connecticut only. Second, the study doesn't directly test demographic or socioeconomic or geographic biases. And lastly, the individual diaries do not model joint trip or household coordinations. So I will close with 3 main points. First, the study demonstrates the zero-shot option for future studies, like public demographic and land use data can ground an LLM well enough to generate travel diaries with measurable scores. Second, the 2 approaches have complementary strengths. The LLM is better at semantic choices, such as purpose and mode, while calibrate models remain strong at counts and timing. Third, the most promising direction is a hybrid architecture, like statistical or machine learning component can constrain trip frequency, scheduling, and feasibility, while the LLM generates conceptually activity and purpose sequence for the areas that we have problems in richness of the data. Thank you for your attention. Any question?
Okay, thank you, Sepehr, for this interesting presentation. There is a first question in the chat. What was the parameter size for Olama?
For the Olama, we use the block groups that the number is 2,143 persons because we had 2,143 block groups. So that was the parameter size we wanted to see for those number of people to generate diaries.
Okay, thank you. Any other question for Sepehr? I have one question regarding the benchmark because there are multiple studies apply deep learning and diffusion model to population synthesis. Did you try those models and compare to LLM zero shot?
Can you ask again the question? I want to make sure that I got it perfectly because I'm reading at the same time the chat box. So
So I said there are also deep learning approaches like diffusion model apply to this kind of problem, population synthesis. Did you benchmark with those approach also or not?
no, actually, we didn't benchmark with the deep learning approaches. So this proof of concept use conventional and interpretable models as the initial benchmark, like comparing the LLM with advanced machine learning or deep learning approaches using held out survey data is also a really good further steps for this study.
Okay, That is interesting. We have similar project and we try to use LLM for validation, not for solving this problem. So it's very interesting and we can discuss further. Back to the
Absolutely.
chat question, was there any linguistic or free format data that used in LLM?
Was there any linguistic free form data? Well, no, the LLM received only structured demographic and land use information converted into a text prompt. We didn't provide a survey narratives or free text travel diaries or other linguistic data. And for the second question, I'm not sure if I have answered that question completely or not. And for the
You
second
can,
one, how is location choice handled? So the location choice was not modeled explicitly. The LLM received neighborhood level, land use, and accessibility characteristic and generated three purposes, uh, generated the three purposes and the distance, but it didn't select specific destinations or routes. Explicit destination choice is an important for further studies, I believe.
okay. And next question,
Can
can
you
you expand?
expand
Yeah.
on what you mean when you say personal? So for each Connecticut, for the data set that we have for the Connecticut, we have 2,143 census block groups. So we generated one synthetic person whose characteristics were sampled from that block group's ACS distribution. And then we combine that persona with the block group's land use context to generate one weekday diary. So this is the geographic coverage, not a representative of synthetic population within each block group. Like it's going to be a kind of a representative of a person who is living in that block group, if that makes sense.
Okay. Thank you, Sepehr, for the presentation and answering the question. We
Thank
will
you.
now continue with the fourth presentation from Jiangbo Yu that present recent development of AI agent across transportation system life cycle review and implications. Jiangbo,
Great.
whenever
Yeah.
you're ready, please
Thank,
go ahead.
great. Thank you very much. So let me just really quickly make sure. Can you see my screen?
Yes.
Great. Yeah. Thank you very much for having me. My name is Jiangbo, and I'm a assistant professor at McGill University, and in the Department of Civil Engineering. And then my talk is a little bit different style than the previous researchers. This is more for a overview of the recent development of AI agents. I think this is kind of important for us to explore earlier because as the AI agents are quickly entering our society, including transportation systems. Um, and we know like transportation systems right now, or has been in the past few thousand years, have been always a result of human machine interactions. Human have been inventing and utilizing machines for transportation purposes for a long time. And it's just that right now where there's this tendency that seems like the machines are becoming changing from a more sort of a passive tool used by humans and turning into a more active participants where the machines and the humans and machines are actually kind of collaboratively forming and enabling mobility services. Um, and because this term is a relatively already kind of common, but I still want to give a background context. So the AI systems right now, what I mean by AI systems start exhibiting agency, or a more general term is agentic AI paradigm, is it's referring to this kind of the AI systems capacity for goal formation and interpretation, strategic actions, and taking goal-oriented actions or purposeful actions. And then they can do social engagement. They can use and they can realize their own inefficiency and then insufficiency, and then they can know, okay, this is the time that my own information is not enough. I need external tools or resources, and they can leverage those to realize certain goals. And at the same time, they can also they can do self-reflection and adaptation. Those agencies are used to be only humans and institutions or organizations have that. But now we started seeing the machines actually start to have that as well. But because of this, it's almost inevitable that we need to study AI agents in a quote-unquote closed loop, where we need to actively consider how the AI systems interact with the environment, whether that's the actual physical reality or a digital twin. Only this way we can understand the behavior of AI agents. We can't just only look at the model itself anymore to know what's actually what we mean by a good model. So the term agency or agentic has a deep philosophical and psychological origins, just like many other AI terms. Like neural network, initially is actually started from psychology. And now the computer scientists, they borrow the term and then call it a neural network. They don't even call them artificial neural network anymore. They simply just call it neural network. But this agentic, this term is also originally from philosophy and psychology. I highly recommend Professor Albert Bandura's work. He has a paper, very influential, extremely influential paper called Agentic Foundation for Social Cognitive Theory. I highly recommend. It's just in 2024. This term is popularized by Professor Andrew Ng in his presentation. His goal is mostly actually just to settle or address a common debate in AI about whether we can call AI systems as an agent. So his argument is, or his solution is, how about we stop arguing about whether a system is an agent, instead we're focusing on making the system more and more agentic. So that's kind of why this term comes out, and it turns out to be quite popular right now. Like a lot of people are using in different industries. I'd also want to slightly clarify on the difference between generative AI and agentic AI. In the generative AI era or paradigm, we have mostly a AI system that is reactive. So we provide the prompts or inputs and then image or things like that and then the output is a reactive, right? Based on the prompt, the output will be a text image or human choice or predicted choice or things like that. It's all generated content. But in agentic AI, the AI system actually can be proactive. It has its own goal or interpret external goals, and it can actually decompose the goals into tasks and trying to realize this. And during the process, if there's any problems or new situations, it can adapt. So one analogy, I think it's not entirely rigorous, but I think it's helpful, is we can think about the generative AI, especially the multimodal, like large language model, like vision language action models, like an engine or a motor, right? And then the agentic AI, in a sense, is kind of the car or the truck or the vehicle or the bus. So clearly the bus or the vehicle is empowered by engine or motors in electric vehicles. But saying that the motor or the engine is the car, it's just not right? And not to mention, in terms of agentic AI, the more appropriate analogy would be a car plus the supporting infrastructure, right? The bus stops and traffic signals. Since like they're collaborative, they're in an aggregate manner to make mobility come into reality. So another confusion is usually the term agency and autonomy. These two terms are clearly intertwined. But what we propose to think about this, conceptualize this, is to think about it as a two-dimensional orthogonal dimensions. One is the machine agency in the x-axis, and then the y-axis is the machine autonomy. The agency is more about purposeful actions and adaptations, And then the autonomy is more about the self-execution, self-governance without external control, right? So the autonomy, this term comes Greek, that auto means self, and then the nomi means law or govern. So the autonomy means the self-governing without external control. So if we look at this way, we can actually classify machines into roughly 4 categories, or say 9 categories. But those are machines that are relatively low in agency and low autonomy. That's more like traditional tools and machines, like a hammer or a bicycle, And at the same time, we have those machines that are more automated, but it's very low in agency, right? Like an automated vacuum cleaner, I would say it's pretty automated, but it's hard to say it's reasoning really, right? And a zombie probably is another less rigorous example. Zombie is certainly autonomously can like moving around, but saying that they have reasoning capabilities and they have their they have a goal or I can solve a very complicated problem, it's certainly an overstatement. At the same time, we have the machine agency, machines that have very high agency, but a very low autonomy. That would be like very sophisticated AI agent or chatbot, but it can provide very sophisticated recommendations, but it doesn't really have the tool or resources to actually make a decision, to actually implement the decision, right? But at the end, now we have this emergence of agentic autonomous machines that is not only has the intention or interpret or form intentions, but also can actually execute them. So we can see that in the industry now, there's 2 general strategies of developing this. One is to develop the machines gradually in the make it autonomous first, and then increase its agency. And or there's that's like would be the company like Waymo and some other companies. They're adding AI agents directly into their autonomous vehicles to let the car not only can drive but also can talk with people. But also we can see another strategy that's like Google and Qualcomm recently Google, Qualcomm, they recently formed the collaboration of adding AI agents directly into manual-driven cars. So that will be like adding the manual-driven cars, make them more autonomous, make them more agentic first, and then make them autonomous. But no matter what, from a transportation researcher's perspective, certainly it's not like the higher the autonomy and the agency, the better. We want to find a sweet spot, right? Certainly the extremely high autonomy is really, really not necessarily good because we want the humans to be the influence to be influenceable, right? We want the machines to be influenceable by humans. So we don't want the machines to be totally autonomous in a way that is completely can govern themselves without the need of human input at all. But at the same time, it's true that having certain systems or processes to be automated is definitely helpful and very convenient, can be. So this is kind of where how we can fine tune this using a 2 kind of dimensional case, have both the autonomy and agency. So if we look at the news, we already see a lot of applications like in the industry and practice of adding AI agents or agentic AI into the transportation, long-term transportation planning, governance, construction, asset monitoring, and then the Google recently announced the capability of agentic capability into their Google Map, so that it's not only giving information but actually can do things for you, like booking hotels and flights, and it gives suggestions on the plans, and then they make coordination with the hotel and the flights. And then the NVIDIA and then many other companies now adding AI agents directly into the cars, either manual-driven cars or autonomous cars, autonomous vehicles. And then we can also see in the logistics domain where people are using AI agents to help improve the logistics and the supply chains. So if we kind of see this trend, we can already conceptualize this idea in transportation systems as a network of AI agents. They're interacting, not necessarily collaborating. Hopefully they're collaborating, but at least we can see them as interacting AI agents. On one hand, they can provide services and give information and eliciting feedback from the actual system users. At the same time, they can actually facilitate the long-term strategic planning and design and the daily operation with through interaction with the human stakeholder and non-technical, technical and non-technical stakeholders. On the other hand, they can they can conduct design, control, operation, and management of the actual public and private mobility services. And also they can plan, construct, investigate, and upgrade and decommission the actual physical transportation infrastructure. So of course, our goal as a researcher is to aim at making sure that the future mobility services are actually providing services to humans, not for the AI agents. Here we're calling this part of AI agents plus the transportation systems as the agentic transportation systems. In the paper in 2025, we report the literature review on the pre-agentic era of through the lens of human-machine interactions in transportation systems, and we find roughly 4 categories of literature: the human-machine collaborative forecasting, analysis, and planning, the human-machine collaborative infrastructure asset construction and management, and then the human-machine collaborative use and the consumption of mobility services and public transportation infrastructure, and the collaborative human-machine collaborative control and operation of vehicles and mobility services. So those have been the literature are pretty quite a lot, and then we can clearly see this pattern. And our hypothesis is, or postulate is, in the agentic era, we're going to develop AI agents around these 4 categories of areas as well. So that's kind of why we're right now, me, my collaborators, my students, my postdocs and I are working on. We are working on developing AI agents to actively and passively collect data from the public or from the experts to understand their opinions and preferences for demand forecasting, for participatory long-term planning. And then at the same time, we're developing AI agents plus the using the digital twin of cities, plus large language model and reinforcement learning for long-term infrastructure planning. And then we're hoping these 2 processes, the demand forecasting and analysis process, and then the long-term infrastructure planning aspects, can be really form a new type of transportation planning process, where we really have this coordinated process where the infrastructure is developed in response to the demand and influencing the demand. At the same time, the demand can be influenced by the infrastructure as a policy lever. And at the same time, the demand can guide the development of the infrastructure planning. And another area is the infrastructure asset construction, monitoring, maintenance, and repair. And we're also actively working on it. It's not entirely my research focus, but certainly we do have, through collaboration with people in Hong Kong and a few other places, we're exploring that areas as well. And then another area is the add of AI agents into vehicles for the operation control and governance. As I already mentioned, there's this is a new phenomena in the industry where the vehicles exhibit a level of agency that is not previously entailed by the term vehicle autonomy, at least by the ICE definition, where in those agentic vehicles, they have the ability for ethical reasoning, interaction, the external tool use, and the system integration, and it can communicate with humans and other agentic machines. And in one concrete case could be like a passenger in autonomous vehicles. If they have a heart attack, the vehicles don't know the context, so they will continue driving to the destination, maybe a restaurant. But in the agentic vehicle, it's actually going to make a judgment. Right? In this case, the human cannot give me the instructions, so I have to make a decision on my own. And once they make a decision to say cancel the reservation in the restaurant, and then I'm going to the hospital instead, and then they can actually the vehicle can actually call the hospital and then to let the emergency room know in advance, and maybe find a better route that it has a smoother pavement, and then maybe call the family members to inform them in advance. So those things are certainly contained by the word agency, but not is not conflicting with autonomy, but it's certainly not conveyed by the autonomy this term. So we are also proposing this different level, just like autonomy. We potentially have this different trajectory of developing the agency in the vehicle, and eventually we're hoping that the agentic vehicles can be an integrated, very important component of our transportation or our future mobility systems. And we already see the Google and Concom right now are developing this, embedding agentic AI directly into their manual-driven cars. And Sanghang is another company that mostly focusing on using the AI agents for schedule vehicle maintenance and maybe changing tire or changing oil, make an oil change. And Tensor and Lyft are actively rolling the first generation of shared agentic vehicles. So that the vehicle not only can drive themselves, but also can interact with the passengers and understand their needs. And here, I think it's another example of the recent news in San Francisco, which I think is calling for the vehicles to really understand better about the context rather than purely just the task execution machine. And so that's kind of you probably already noticed, some of you, the rise of the term vision language model, vision language action model for autonomous driving. So it's really fundamentally about making sure the vehicle has some level of agency to understand the context. And then, of course, the agentic vehicles have these potential cyber security concerns that my postdoc, Ali Islami, is right now actively exploring with our collaborator in Europe. And for the fourth category, we're also actively looking for the agentic mobility services, how the AI agents or agentic AI can help better manage the fleet, rather than the shared autonomous mobility fleet, or the actual mixed traffic with both manual-driven and autonomous vehicles. So our question is, in terms of the conference, bridging transportation researchers, what are other researchers' efforts in this agentic era? So we did a literature review quickly in the for the past 3-4 years, from 2023 to the 2026 quarter one, for Transportation Journal. By Transportation Journal, I'm quite specific. I'm talking about journals that has the term transport or transportation, right? I think that's roughly captured most of the well-recognized transportation journals, like Transportation Part A to F, and then Transport Policy, IEEE Intelligent Transportation Systems, right? And then Transport Geography, things like that. And we find roughly about 300 something articles, and then we go through a rigorous process of reviewing this from the abstract and title to the actual full text, and then we kind of narrow it down to 100 or roughly 100 articles. And then we find that clearly there is a significant increase, right? From 2023, there's 1 articles, and then 2025 is already 63. And in 2026, so only first quarter is already 42 articles. And recently, I definitely know there's a lot more in the second quarter and third quarter. And then the 2 most common journal for this type of research is IEEE Intelligent Transactions on Intelligent Transportation Systems and Transportation Research Part C. And then there is four major, and we've noticed that the 4 major applications are also pretty still applicable for the 4 categories. So we kind of just did the literature review, and you can check our articles if you want, for the planning aspect, for the infrastructure domain, for the agency, the vehicle aspect, and then for the fleet and the traffic management aspect. And then the preliminary conclusion is that the AI agents or agentic AI in this transportation domain is quite still preliminary and early stage, understandable. And then so I think it's a good time to do this proactively, to not only really learn things from the generative AI era, but at the same time really recognize that a good AI agents doesn't necessarily mean a good transportation systems. So we should shift our question not only to from the model, whether the model performs well, to whether the coupled translation systems improve over time. So we're proposing this justifiable, inclusive, and adaptable principles that can guide our potential development. And we're hoping that in the future, we're active as translation researchers, open-minded ones, to embrace this agentic era, but carefully. And I really appreciate your time. And please let me know if you have any questions. And then you can also check our work and then other works that we look at in the literature review. Thank you very much.
Thank you very much for this interesting presentation, Jiangbo. You give a very clear overview, touch many topics. Thank you very much. So I let you read the question of Professor Kakelman in the chat. Please feel free to put your questions in the chat.
Wait. So the sorry, I think the first question from Professor Kakelman is to avoid more chaos and rider cost on our roadways. How do you? Sorry, is that the first question? Sorry.
I think so.
Yes.
That's the one he's referring to.
Oh, great. Thank you. How do you recommend we get people to share robo-taxi rides with people they don't know? There are cameras, 911 buttons, etc., but we still have issues. We're doing background, sorry, just blocked. We're doing background checks for riders opt-in for social network, like McGill University students only rides. Big buses, road user tolls, incentive transit type credits for those who share rides, etc. Either way, I'm not sure I know this. I think right now the kind of a related connect this with the agentic era. I think this is kind of the question that we're trying to address, right? And then so right now all of these problems to avoid more chaos on our roadways is in a sense the perceived chaos is a result of the agency of humans and then the public institutions and the companies right now, and we're adding one more actor, which is the machine agents. So we can design the machine agents in a way that can reduce the chaos, but also but without managing it well or proactively. We're adding a new type of agents that can, or the type of agency that can actually make the system even worse. And how do I recommend we get people to share? I think one way I can immediately think about is to use AI agents to actually actively engage with humans to know their each individual's life needs, and then really use language or just a natural conversation to kind of, if it is helpful for to share robo-taxi rides, and they can actually convey this opinion in a personalized use, so with a natural language, in a language that they can understand. So I think this is something that's not there in the past. It's more like everybody use the app, and then this app you can share the rides with a robot taxi or human-driven cars, vehicles. But I think that could be an opportunity. And so I think so with the agentic AI, there's a possibility that we no longer need to click buttons, and then we just really interacting with just like a friend, and who will really think about our needs and hopefully fits our agenda and our goals. So that's hopefully I'm answering generally the question.
Yes, thank you. The next one is, what are your thoughts about potential conflict between the agentic AI and individual freedom of choice?
I really like this type of question. But in a sense, it's not a new problem, right? Because right now the society we have a lot of different types of agencies by other peoples and by the governments, by other organizations, and then so the potential conflicts between those organizations and people who have agency and our own individual freedom of choice always been a problem, right? There's a lot of philosophical and psychological literature on this topic, and I personally don't particularly see there's anything really truly new, right? There's always a problem with this, like whether the agentic state, like in the psychology like to call it, as whether we are truly in our free form, or we have freedom of choice, or we are actually in the agentic state that it's actually just act on behalf of other people. It's very likely, right? And then I don't have a solution for this, but I do think my thoughts really is just let's work on it, but this is the old problems, but it's because of the agentic AI, it's becoming more eminent. So that's
Thank you.
yeah.
Just to add one question on top of it, from the legal aspect, if the AI agents do some violation or something wrong legally, or push the button in a wrong way, who is responsible?
Yeah, and I think that's kind of the key question of this. Right now, I think we have a active designer of the agentic system, so that they could be the one that potentially be responsible for. But in the future, this kind of line is getting blurred. I know in Canada government, they already launched a guideline for using agentic AI. And I know Europe is actively updating their AI Action Act, the AI Act. So many countries and regions are right now actively catching up to develop new guidelines and legal frameworks for this. So I encourage you to check it out. And I'm not in the legal field, so I don't have a particular
Okay.
strong opinion about this.
And last question, what is the potential of using AI agents for real-time online ride pooling compared to DQN-based policies?
I think we're talking about, in my opinion, we're talking about different layers of the network. I think the AI agents, again, they have agency to use tools. They can, if they decided that the DQN based policies is useful, they can use those DQN policies, right? So there's absolutely no conflicts. So but the AI, if the AI agents think that is not explainable or is necessary for using transparent framework, interpretable framework, and the AI agents can actually do that as well. The goal here is about who is making for the system level objective, which is probably something like reduce travel time, emission, making sure that it's equitable and inclusive. Those things that can either be set by AI agents or by the policymakers or humans. But how to actually achieve that is more about the agentic workflow, that if AI agents decide that DQN policies or some other deep neural network is usable in particular case, they can do that. So yeah, it's they're not alternatives to each other. The agentic AI can use different type of tools.
Okay, thank you very much. We can move to the next presenter. The fifth and final presentation by Onindo, Akash, Shuvro, that present IntelliSUMO, simulating the traffic impact of bridge closure using a large language model powered framework. Onindo, if you're ready, please go ahead. You are yeah, now it's fine.
So, can you hear me?
Yes.
Okay. Hello everyone. So today I'm Onindo Shuvro. I'm a graduate student from Florida A&M University. So today I'll present IntelliSUMO simulating the traffic impact of bridge closure using a large language model powered framework. So my co-authors are Dr. Alison Sevim, Rumin K, Dr. Shannon Vivian Gu, and Dr. Irman Ozguven. So from background, so to begin, let's look at the core challenge, like bridge closure, whether it is from plant maintenance or sudden failures, it causes severe traffic disruption. So planners need to optimize traffic for planned events and predict consequences fast, so that they can make a contingency plans. And the traditional simulation tools require deep technical expertise. They need significant time to model the scenario, so they hinder the both proactive planning and rapid responses. So these are the evidence from the previous preschool scenario from Kujira et al. Like the Richmond San Rafael Bridge was closed in San Francisco Bay Area, and 9 unplanned closure created additional 14,000 vehicle hours delay and 600,000 extra vehicle miles travels, and around 55,000 plus trips affected. And there are other scenarios in Center Street Bridge, and 14-month bridge closure scenario created around 4.4% reduction in the daily traffic flows, and morning peak hour shifted around 15 minutes earlier. So for this, we need rapid, accessible, and high fidelity tools for contingency planning and incident response before, during, and after a closure scenario. So the critical question is, like, when a major bridge closes, authority needs immediate answers, like where will the traffic go, then which alternate routes will be most affected, and what are the new delay times, what will be the new bottlenecks, where will the new bottleneck will emerge, and what will be the new hotspots, and what is the environmental fallout in terms of fuel consumption or emissions. So our vision is like a conversational solution. It's IntelliSUMO. Like, you can just simply ask, like, simulate the closure of the, like, any bridge, like Patron Bridge during the rush hour. So our goal is to use a large language model to translate our simple human language into a complex executable traffic simulations. Like in traditional workflow, like different persons need to do different works, like network preparation, traffic data analysis, demand or routing, or like traffic simulation and calibration validation, and other the output analysis, visualization, and report making. So we want to do into a single conversational solutions for the planners. So prior studies for traffic LLMs for traffic simulation, there are some studies like ChatSumo, OpenTI, and Sumo MCP, ChatSumo agent. These are the most relevant studies related to our work, and they actually used large language model in the ChatSumo. They use large language model to generate the network using from OpenStreetMap and Sumo network generate, and created the trips, and they mainly worked on the intersections, like how to analyze the density, travel time, or emissions for those intersections, and those are for actually short, small size networks. And in the OpenTI, they actually connects the LLM with traffic simulation, optimization, and data analysis, and they had created a they actually interpret the user intent and created a pool of tools, and it was a modular system and depends on the predefined tool sets, and they couldn't adaptively discover the tools. And in the Sumo MCP, they actually created the model context protocol. They build a model context protocol MCP and connects it with the AI agents, and through JSON RPC messaging, they could dynamically discover, import, or orchestrate Sumo tools, and they can flexibly call tools in a sequence and generate structure reports automatically. So combining these ideas, but we found some research gap, like there was no disruption related modeling, like primarily designed for general. Previously, it was primarily designed for general simulation or signal optimization, no explicitly paired baseline for baseline versus closure scenario, or limited decision-oriented outputs, like what will be the rerouting corridors, congestion hotspots, or emission changes, and there was limited auditability and reproducibility. So, and also another technical bottleneck is like Sumo can be used for like complex disruption scenario generation, but it requires technical expertise and requires a lot of time. So that's a bottleneck. So, sorry. So formalizing our disruption problem. So let G equals to V E, it denotes the directed road network where the V is for the set of nodes and E is for the set of directed edges, and a disruption is specified by a closure set E sub T, which is a subset of E, and the disruption network is G prime. Given a fixed origin destination demand realization D, a fixed random seed was omega, and we let S pi GDW or GD omega that denote the trajectory set produced by a sumo run on the network G with rerouting policing pi, and the disruption impact is a differential of a performance function phi. So holding D and omega fixed, we isolate the disruption effect from the stochastic variation in demand realization, and del phi reflects only the network change caused by the closure. So this is for the closure. So what are the performance functionals? The average trip travel time, mean network speed, edge level density, queue length, and emissions on the monitored edges. So what are our framework? This diagram shows our IntelliSUMO framework. So first, an user can, in the interface, it can ask like, I want to see the traffic simulation of city of Miami when Brickell Avenue Beach become closed. So there should be the user input, and this intent, this user input will connect, will go to the LLM, and it will do the intent analysis and extract the intentions, like the actions will be the close bridge, target will be the Brickell Beach Avenue, or the location will be the Miami, Florida. Then it will discover the available tools in the for the MCP server, and also do the tool routing. Then it will do the and this part is like the reasoning layer. So for our reasoning layer, we have local llama 3.18b, and that will do the intent extraction, workflow planning, and result synthesis. And then we have in the second part that simulation generation, that can be from two part, like from the abstract network or the real world network. So from the real world, for real world network, like there is OSM get.py tool for it will download the OSM network, OpenStreetMap network, and convert it to using the net convert, and it will create a network XML file that will be used in the Sumo. And for the route generation, there is, like, if there is OD matrix, it will use OD to trips.py, and or if there is synthetic demand, it will use random trips.py. And there are detectors and those are connected to create the network XML file, route XML file, additional XML file, and the Sumo configuration files. And there is Sumo simulation modification tools also, that like for vehicle modification, traffic signal optimization, like TLS cycle adaptation or traffic light signal coordination. These tools are also there. And after combining those tools, there will be the Sumo executions, like that can be run by Sumo GUI or Tracy runner. So, and it will create, after the simulation run, it will create it creates the like the outputs into trip info and the emissions or the log files, and then those results are visualized, then outputs are analyzed, and their density analysis, travel time analysis, and emission analysis, and those are done by the LLMs. So there are actually three layers. So reasoning layer, orchestration layers. In the orchestration layer is the middle part, that model context protocol. It serves the dynamic and auditable tool dispatch via JSON RPC messaging. And in the execution part, this part, the Sumo plus Tracy scenario, and that creates the network paired baseline closure simulation runs. So what I explained, like the reasoning layer, it performs the intent extraction into a structured tuple, like action, targeted infrastructure, location, parameters, or monitoring, then workflow planning, intermediate result reasoning that updates the plant, and result synthesis into a narrative aligned with the disruption response questions. And in the orchestration layer, they like it does the network mapping, demand generation, simulation execution, signal optimization, network edits, analysis, and they have the MCP tools for there for JSON, and using JSON RPC dispatch, it gives a dynamic discovery structure and full auditability. And there is also execution in the execution layer, like we use the OSM, net convert, net generate, and other tools, and creates the baseline versus closure scenario. So how it works from watch to virtual world, if we simplify, like user request will be like what happens if Brickell Avenue bridge is closed. It will intent extraction, like close bridge, Brickell Avenue bridge, and location will be the Miami, Florida. It will identify the intent extraction, then simulation will be generated. There will be certain tools in the background that will do it, like and if you ask the identifies and removes the bridge road segments, which road segments to be like closed, and then it will like analysis will be done after the simulation run. The analysis will be done, the travel time, density, emissions, and summarize the key findings in the human readable report. And then there will be the customization, like follow-up questions you can ask, like what if the closure starts an hour earlier, or also close the bridge southbound only. Then it will use the like execution cycle, like the request is passed into an structured intent table again, and then planning next actions are planned from the current project state plus intent. Then again executions, like selected MCP tools run SUMO executes the simulation, and then response composition again. So this cycle is done. And what are the interfaces? So we created a web-based chat interface for non-technical use, and also we can input those an ID interface for cursor, so you can modify there the codes if you want. The case study for this case study, we did a case study for MacArthur Causeway closure, like the normal network operations, the baseline scenario, and the closure scenario is like the MacArthur Causeway closed, and dynamic rerouting enabled that time. So this is the chat interface for our case. And after we did a prompt like close MacArthur Causeway in Miami radius 3 kilometer, run closure scenario simulation for 1 hour with 2000 vehicle, monitor any suitable 5 edges, and compare baseline versus closure scenario, and run the simulation with GUI. So with or without GUI, you can do that. So it will like extract the information, find the location, and download the network. This is the network they downloaded. And then from OpenStreetMap to SUMO, it actually used this part. And after that, they like produce this kind of results, like trip duration distribution for the baseline versus the closure scenario, and network level performances. So right now, like average trip time, mean speed, the like average trip time increased by for the closure scenario like 16.9%, and the mean speed reduced by 4.4%. So what are the like there is a limitation, like the currently we actually place detectors on the 5 edges I in the prompt, so it catches the immediate vicinity of the closed bridges for no vehicles traverse those edges in the closure scenario. That's why these monitored edge values are not the actual network wide emission data. So the bottom the network wide metrics like this average trip time or mean speed are the produce the truer picture of the system level impact. But there are some limitations here, like when we try to monitor the whole network, the logs are to become so huge, like there are around 40,000 edges, so monitoring all the edges is a problem. So there needs fine tuning in our analysis in this part. So based on trajectory heat map is there, also it can produce. And into the discussion is like the network acquisition, the disruption encoding, demand generation, paired execution, this kind of work it can done, and monitor edge metrics such as the local carbon dioxide reduction are not network-wide quantities. That's the part here we showed. And results are right now preliminary based on the synthetic demand. It's need and with limited edge level monitoring. So we need the calibrated OD matrices and larger networks, longer horizons, and multiple demands, multimodal demand for the realistic scenario generation is needed for the validation. Right now, it's preliminary results. The frameworks already lowers the technical barrier, but we need other integration. So for the MacArthur Causeway case study, we found that the closer increased average trip time by 16.9% for the monitorages for the synthetic demand. So and also traffic rerouted in the SUMO view, that it showed that traffic rerouted toward the Venetian Causeway in the and adjacent corridors. And in these cases, like IntelliSUMO that integrates the natural language understanding and model context protocol, and it could formalize the disruption analysis as a paired scenario problem and MCP mediate workflow that replaces manual scripting with structured tool invocations. So overall, it can do the disruption modeling more accessible for transportation agencies and emergency responders. So what are the future directions in our cases? Like we are planning to do hierarchical and graph-based planning for more efficient scenario executions and decision making, and creating dashboards for experiment design, parameter modification, and real-time visualization, and multi-agent collaborations like parallel agents for do parallel works like scenario generation, rerouting, and optimization, and dynamic MCP resource management, improve multimodal modeling. Like right now, it's only there is cars. For realistic representation for the intersection, transit, or pedestrian and bicycles should how they work, and standard is benchmarking. Like now, we haven't benchmarked like the common data sets for matrix validity, convergence, scalability, and performance comparisons for different cities and different scenarios, and also multimodal interactions like interactions for integration of maps, images, and voice and visual analytics for the improved usability and interpretations. So this work is supported by like a FIU Innovation Bridge Technology IBT ABC UTC project. So this project is like IntelliBridge simulating the traffic impact of bridge closure using a large language model powered framework and by the USDOT, and also supported by National Natural Science of Foundation by the USDOT ACTS Center, and also the Rural Safe Efficient Advanced Transportation Center by the USDOT grant. Thank you. If you have any question, feel free to
Okay.
ask.
Thank you very much, Onindo, for this interesting presentation. We have one question, two questions in the chat.
Okay.
The first one is, could the AI workflow you showed with MCP and SUMO be used to automatically iteratively calibrate a micro simulation to match
Automatically calibrate.
existing condition?
So right now we actually tried, but the automatically calibration is not we couldn't actually automatically calibrate this. So you need to be for every scenario, every city or every location, you need to calibrate it personally. But we can we have those parameters like SUMO parameters. So we are trying to calibrate it for Miami city. So for the similar cities, those parameters, you can just change those parameters according to your city. So, but you couldn't do the automatically calibrate. So we haven't fully calibrated for the Miami city right now. So we are trying to calibrate it. That's why we use the synthetic data. And for the second question, ChatSUMO paper and the pros and cons on IntelliSUMO and ChatSUMO. So we are actually connected with the ChatSUMO author. One of the authors is Rumin case from the ChatSUMO paper, and we are collaborated with Xiang Lui and Dr. Azhar of the ChatSUMO papers. So, and the main pros and cons is like that for ChatSUMO, is the app for ChatSUMO and ChatSUMO agent paper, and like they are used for the only small networks, like they haven't for the used for the whole network level. So they are just asked if you want to go from one location from the another location, if it can do or not. So this kind of scenario generation. So but for the disruption level generations, it requires the large network size, and also requires validations, and like if you increase the network size, the simulation time increases. And for the ChatSUMO paper, their simulation time is very low because it's only for one directional use, like from one location from another. They created, it was the first paper for this kind of a scenario, so that's why this this is the basis from where we get the idea, and from we are
Okay.
working on to expand it into a large network
Thank
level.
you very much. Thank you. I have one more question. So based on my experience with Sumo, converting OSM network to the Sumo network, it might cause a lot of issues with the traffic signals, with the number of lanes, but you didn't really mention the supply calibration. How do you be sure that your network is good enough, accurate enough? And also Sumo has some sort of facilitating configuration like teleporting, or Tracy sometimes can be over smoothing the traffic. So how do you deal with these kind of issues?
So we are actually dealing with these issues. Like actually first uh, we generated a same scenario for the Miami road close Miami city, and using those parameters, like we found some these parameters that are like similar, and using those like there are say seven like the network what you told, like the networks level parameters, those parameters we actually show that, and it actually happens like teleporting and the smoothing in most of the cases. So right now it's like first it's not calibrated, or not the actual scenario. It's just the simulation can run, and we can get the visualizations, and we can get the all the things, but the background needs to be calibrated, and further.
Okay, thank you very much. There is one more. Okay, so
Thank you.
thank you for the presentation. This brings us to the end of this session. So we had a very nice range of presentation about AI data-driven methods. So I would like to thank the presenters again and everyone who joined the session and participation in the discussion. Thank you very much, and I hope you have a good conference and enjoy the rest of the day.